Good afternoon, students. Welcome to lecture number 14, the foundations of reinforcement learning. It is a branch of machine learning which is relatively novel and finds many practical applications. The list of agenda items include basics of reinforcement learning, and we shall define certain terms such as action, reward, punishment, expected accumulated reward, and policy. And then the list also includes two foundational algorithms of machine learning called the value iteration and the policy iteration. And I would like to conclude our lecture with a brief introduction to the Q-learning. All right, so let's get started with the reinforcement learning foundations. Reinforcement learning is a more natural paradigm of learning where inputs are generally the actions and the output is reward or punishment that our agent is going to earn as a consequence of those actions. Now, it is a realistic mechanism to train our system to learn and to adapt to several real-life scenarios, which include state-of-the-art examples such as training the self-driving cars. And it also finds a natural connection with training computers to play games such as chess and cards. So in some sense, reinforcement learning encapsulates the true spirit of the learning that we human beings are familiar with. And in that sense, it adequately captures a wide range of problems that we encounter in real-life machine learning problems. Let's start with a simple example of a robot moving in an arena represented by a 2D grid. There are as many as 12 grid cells represented by 4 by 3 2D grid. So essentially we have 4 columns and 3 rows. So our robot, as it moves through the arena, it receives some reward or punishment depending upon its location in the grid, represented by X and Y. So X represents the column number and Y represents the row number at any time t. Now, in terms of actions, the robot can apparently take 4 different types of action. So robot can move up in the arena, it can move down, it can turn left, it can turn right. However, note that there is another action that we shall add later to this list. And by means of this action, the robot can move to an adjacent cell in the next time instant, which is t plus 1. Now, an important assumption about this variable rxy, this is actually not a variable, it is a way to represent the reward or the punishment. It is going to be some number that is not going to change with time. So that's a very important assumption about rxy, which represents the reward and the punishment in the grid cell. And we also assume that we have a perfect knowledge of rxy. That is, we have no ambiguity or uncertainty in the value of the reward and the punishment that the robot receives or earns in any grid cell. So our information about the arena is perfect. The arena contains 2 terminal states at 4, 3 and 4, 2. So here and here, and they have their corresponding rewards. So in case of 4, 3, the reward is plus 1, and in case of 4, 2, the reward is minus 1. Now the game ends as soon as the robot enters in either terminal state. And our job is to quantify the performance of the robot by accumulating all the rewards that the robot has earned to reach the terminal state. So for instance, if a robot starts here in state 1, 1 and it follows certain path to reach this terminal state represented by 4, 3, so then we would like to add up all the rewards that the robot has earned in R11 as R12, R13, R23 and R33. So all of them are going to add up, and that would be the net reward. Now let us set the reward Rxy equals to minus 0.04 for all the states except the terminal states, and obviously we are not associating any reward with the obstacle cell at 2, 2, considering that the robot has to avoid this obstacle anyways. The initial location of the robot is 1, 1. So if the robot starts in state 1, 1 and then it follows a path like this, that is, it goes from 1, 1 to 1, 2, then 1, 3, then 2, 3, 3, 3 and 4, 3. So the path is indicated here, and it will end up in the terminal state where the reward is plus 1. So the accumulated reward will be minus 0.04 times 5 plus 1, that's 0.8. And the interesting thing to note is that the accumulated reward is positive in this example. However, if the robot follows a different path starting in the same initial state as before, but the path is different, so it goes 1, 1, 2, 1, 3, 1, 4, 1 and ends up in 4, 2. So the path would be this. Now in this case it goes through 4 grid cells where it is going to earn minus 0.04 reward, and the reward in the terminal state is minus 1, so the accumulated reward is minus 1.16, which is negative in this case. Let us define a term called policy. So policy is a series of actions taken by a robot. So if a robot starts in the initial state 1, 1, then we saw in the previous 2 examples, in the first case the robot moved up and then it goes up again, and then it turned right, and again it moved right to reach the terminal state, and it gave a positive reward of plus 0.8. The other policy was the robot moved to its right, again right, and then it went up, where the accumulated reward was negative, minus 1.16. And you can consider this negative reward as a punishment to the robot, or the punishment the robot has seen. So apparently, if you compare the 2 rewards, you can say that the first policy is a probably better policy because it is going to give us a positive reward. So it raises an important question that what policy is going to give us the maximum positive reward if we lift the restriction on the duration of the game. That is to say, let us not bound our robot to reach the terminal states in finite number of action or steps. In other words, if we let loose our robot in this arena, then the robot has a choice to keep on moving and not terminate its journey in any one of the terminal states. Then the answer to this question is that the policy strongly depends on the value of Rxy, the reward in each grid cell. And it's because, for instance, if RxY is positive, then the robot can keep on moving between these non-terminal grid cells, and it may never wish to terminate its navigation or journey, because the net reward is always positive and it is always growing. So the robot has no incentive to end its navigation or end this game. If, however, the RxY value is negative, then the situation will obviously be different. So let's look at some of the scenarios in which, for different values of RxY, the strategy or the policy of the robot differs. But before that, we have to define some notation here for the actions. So the up arrow means up, down arrow means down, and then right arrow corresponds to right, and the left arrow corresponds to the left. We are, however, adding a new action, which is stay put. Means that we are instructing robot do not move. So the robot is going to stay in the same grid cell. Further simplification is that RxY value for all the grid cells except the obstacle cell and the terminal cell is the same, and it is going to be some constant number, and we shall see that example in the next slide. And we wish to find the policy that maximizes our reward for the given initial state x, y. Right? So we shall ask that if a robot is let loose in this arena in any initial state, then what is the best action it can take in that grid cell? And quite naturally, that answer would depend on the value of RxY, which, by the way, is same for all the grid cells, and that value is set equals to R. So the example that we are going to see in the next slide, we're going to use this value of R, which is the reward in all the grid cells except for the terminal state and the obstacle state or the cell at 2, 2. Before proceeding, an important thing to note is that in principle, any XY state can be the initial state. Obviously, the initial state cannot be the obstacle state or any one of the terminal states. But all other states can be, in principle, the initial state, because we can say that our robot can start its journey even in a state which is very close to the terminal state, let's say 4, 1. Then we wish to find out the best action for each XY state, considering it as the initial state, so that it reflects the policy that maximizes the total reward. Right? So let's take an example and see what do we actually mean by these statements. So this example is taken from the textbook. This is figure 17.2. An important assumption in this example is that the robot doesn't get any negative reward even if it comes in contact with the obstacle. So if a robot is hitting an obstacle, as we shall see some of these cases here, then there is no negative reward, but there is the reward associated with the cell or the state itself that we shall see will vary for these 5 different cases. So keeping that in mind, the other thing to note is that the environment is stochastic, which means that if you instruct the robot to go, let's say, straight, then there is a small probability that the robot may actually go right or left, or it remains in the same cell, or it goes down. But that occurs with the small probabilities, and those are described in the text. So let's look at the first case where R, the reward in all the states, is minus 0.04. So in this case, the policy of the robot is to somehow navigate its way to reach the terminal state where the reward is +1. So we can say that the robot policy is to find the positive reward terminal state wherever it is. So if it is here, it is actually searching for a path that leads to the terminal state +1, and obviously it is avoiding the minus terminal state. But now let's look at a case where the reward of all the states except those of the obstacle and the terminals, if the reward is very negative, which is actually less than -0.162, then the robot would like to terminate the game as quickly as possible because it is really suffering from punishment. So the strategy here is to terminate the game as quickly as possible by accumulating a minimum negative reward. So that is the strategy. So in other words, we can say that the robot life here in this game is very miserable. So wherever the robot starts its navigation, it will just find out the shortest path to the closest terminal state, and it doesn't care if the terminal state reward is +1 or -1. Now the second case, when the reward is a negative number, still a negative number, but the negative number is smaller. It lies between -0.4 and -0.08. So in this case, the strategy will be different. The policy of the robot is different, and the policy is that it will try to stay, it is trying to find a path to the terminal state where the reward is +1. So in some sense, it is not explicitly running away from the minus terminal state, but its preference is to find a path to the terminal state with a +1 reward, and that's how it describes the policy. Now in this case, the value of r is still a negative number, but it's a negative number that's very close to 0. The policy is to avoid this negative state, negative terminal state, and in that pursuit, the robot is even willing to bang its head in the obstacle, and it doesn't mind hitting the boundaries either. And yes, more preferably, if it can reach the plus reward terminal state, it is even better. But the main point to note over here is that the robot is hiding, it's running away from the negative terminal state. And what about this case? We pointed out this case a few minutes ago as well. The reward in all the states is positive except for the terminal states and the obstacle, and so the robot has no incentive whatever to reach any one of these terminal states, because your robot can just keep on moving in this arena and it will keep on gathering the expected positive reward or the accumulated positive reward, and it doesn't have to terminate its game. In fact, the robot has no incentive to reach any one of the terminal state. So 4 different values of R and 4 different strategies, 4 different policies. So let us define our terms more crisply. We say that for each state S, which is represented by x, y, defining the location of the grid cells, we have a policy pi of S. And this policy represents an action, as we saw earlier. It is an action for the robot to take. Now, based upon this policy pi, for all the states, we can compute the net or the expected reward earned by the robot. It is represented as U S naught. superscript pi, where S0 represents the initial state. So the formula for the net reward, and later on we are going to call it expected reward, U pi S0, is actually the sum of the rewards that the robot is going to earn through all the grid cells it has visited, S0, S1, S2, and so on. And remember that this summation may never end, like we saw in the previous case. When the value of R was greater than 0, then there was no incentive for a robot to terminate the game. Some more realistic assumptions go into the reinforcement learning paradigm. One of them is the value of future reward. And we say that the future rewards, the reward that the robot is going to earn in the future as it visits the cells or the states in the future, they are less valuable than the reward that is at hand. As the anecdote says, a bird in the hand is better than two in the bush. Therefore, we discount the rewards, the future rewards, by a factor gamma, and gamma lies between 0 and 1. So the reward earned in a state ST, which is a state the robot is in at time instant t, we're going to multiply that robot by a discount factor, which is gamma to the power t. So our expected accumulated reward is now going to change as follows. It is still a sum of reward, but the future reward have been discounted by gamma square, and for the tth state reward, the discount factor is gamma to the power t. And an important observation is that U by S0 can now be represented recursively. Well, we could have represented it using recursive equation even before including gammas, but because this is the expression we want to proceed with, this whole thing can be represented as gamma times U by S1. So in a sense, we're saying that the expected reward when a robot starts its journey in S0 is equal to the reward in state S0 plus the discounted reward of the robot when it begins its journey in the state S1. And obviously the superscript pi remains intact because the robot is moving according to some policy pi, and therefore this is a recursive expression. The other important assumption is regarding the imprecise control. As we described earlier, that an imprecision in controlling the robot can cause incorrect outcome of the robot action. For instance, if you instruct a robot to go straight up, then the action execution may be imperfect and it may accidentally move robot to left, right, down, or the robot may not move at all. And all of those incorrect consequences describe what we are familiar with, robot motion model. If we incorporate robot motion model uncertainties and imprecise actions, then we need to include these probabilities. So this is probability that the robot in state S0 goes into state S1 prime when the action is A. So again, the conditional probabilities describe our robot motion model. However, note that we are conditioning on two things now: the previous state and the action taken in the previous state, and the probability is over current state. Or you can say we are conditioning over current state and the action taken in the current state, and the probability is of the next state. And so the expression is now changed. We're going to multiply this probability P S1 prime condition on S0 and A multiplied by the expected accumulated reward of state S1 prime, and we are going to add them all up. This addition is over S1 prime. So in some sense we are saying that we are counting the weighted sum of expected accumulated rewards of all the neighboring states where the robot can move to, and the weights are these probabilities described by the robot motion model. So if we take robot motion model into account as well as the discounting factor, the final expression is like this. So we say that the expected accumulated reward when a robot begins its journey in the state S0 is RS0 plus gamma times the weighted sum of expected accumulating rewards of its next immediate or the neighboring states S1 prime, and the weights are actually the probabilities of robot motion model. Our job in reinforcement learning is to find a policy pi, because a robot is moving from one state to another according to some policy. So our job is to find a policy Pysteric that gives us the maximum expected accumulated reward. So that is the problem that the reinforcement learning tries to solve. So before we discuss the algorithms to find the policy that gives maximum expected reward, we have to go through the summary of some important terms as well as the definitions. So A of S describes the action, and in this particular example there are 5 types of action that a robot can take in a state S, and the states are basically defined by the grid cells. So the robot can be in any grid cell at any time except for the obstacle grid cell and the terminal cells of the terminal states. And A of S describes the possible actions that a robot can take. We define pi of S as an action taken by a robot in a state S where it moves according to some policy pi. So while A of S in the previous slide was any action that a robot could take, pi of S specifies an action which is basically dictated by some policy. So if a robot motion has some predefined policy, then if it takes action in accordance with that policy, then that action is represented by pi of S in that state S. Pi is actually a list of policies for all the states. So the difference to note over here is that pi without any preceding brackets or without any affiliation with the state variable such as S, it is actually describing the list of policies of all the states, whereas pi bracket S represents the policy of a specific state. So for instance, your pi may look like a list of actions such as action for the 1 state is to go up, action for the state 1 2 is to go up, action for state 1 3 is to go right, and so on and so forth. So there's a correspondence of action with the states. Next is Pysteric. So this is static. So Pysteric is actually a policy that attains the maximum expected accumulated reward, U pi of s. And U pi of s is, as we've been defining already, is the expected accumulated reward. The word expected comes about because we saw in the expression of U pi of s that includes the probabilities. So therefore the term expected. So it's an expected accumulated reward when a robot initial state is S and it is moving according to the policy pi. Value iteration. So it is a method of computing the optimal policy indirectly by iteratively updating the value of U pi of s till convergence. So remember that value iteration is actually about computing the expected accumulated reward and indirectly calculating the optimal policy. The expression goes like this. We say that for all the states, you have to calculate the value of expected accumulated reward as RS plus gamma times the maximum of, say, n numbers. And each of these n numbers represent some kind of an expected reward as a consequence of an action. So let's say in any state S, we can take up to n different actions. In our example that we saw in the previous slides, we could take up to 5 different actions. So A1, A2 all the way to A5. And then as a consequence of those actions, taking the robot motion model into the account, we get different expected accumulated reward. Expressions have been discussed already. So we have 5 different expected rewards and we choose the one which has the maximum value. And the corresponding action is also important. So the action, so for instance, if A2, this term over here, gives the maximum value, then this value is going to be added with RS after multiplying with the gamma, and A2 will be recorded and it will become the policy for the state. So we do this for all the states, for all the state S. We calculate U pi of s and we note what actions gave us the maximum values of the accumulated reward for each state, and that's how we compute the policy, because policy is just the list of best possible action for all the states. This whole process can be more succinctly represented as this following mathematical expression. We say that for all s, U pi of s will be updated as R of s plus gamma times maximum of this expression, which is same as the one that is written above. But instead of writing A1, A2, AN, we just say A belongs to the set of actions taken in that state. So this is just a brief or a more neat representation of what we have described earlier. The value iteration algorithm, like other machine learning algorithms, has an iterative nature. So we say that we update these u's from ui minus 1. In fact, here we are actually talking about U pi of s, so those superscript have been missing. So U pi of s in the iteration I will be computed from ui minus 1. That is the expected accumulated reward calculated from the previous iterations. So this is the only thing that we store from the iterations of the algorithm. Obviously, the robot motion model is time independent, and the rewards in the states are also time independent. This gamma is also time independent. For the purpose of computation, this superscript representing the policy can be dropped. So we can simplify our notation just by keeping the subscript I or I minus 1, and we're going to drop this pi. And we should bring this pi into account the moment algorithm finishes, because we are already storing the values of action which are giving us the maximum accumulating reward, so they are being stored separately. So another reason to drop this superscript pi is that the optimal policy that we are computing is going to be stored in a separate variable based upon the action which maximize the expected accumulated reward. One can summarize the value iteration algorithm using following pseudocode. And you can find this pseudocode or similar one in the textbook section 17.2 as well. All right, so we start with, we initialize the expected accumulated reward for all the states by some initial values. It can be random. And we're going to repeat an algorithm. So these are the iterations that we've been talking about. So there are going to be iterations, some repetitions, and in each iteration we are going to update the values of expected accumulated rewards from, so there's a variable u prime of s. And how do we calculate this u prime of s? Well, u prime of s is going to be computed from u of s. So this u of s is something which was computed in the previous iteration and now utilized to update the value of u prime of s. And we said that the corresponding actions which maximize this expected accumulated rewards are going to be stored in the policy list or policy vector, whatever you call it. So that's pi of s. So for each state s, we are going to store after updating two numbers. One of them is u prime and the other one is pi. So u represents the updated expected accumulated reward for that state, and pi represents the policy or the optimal updated optimal policy till that point. And obviously these are going to be updated as we go through the iterations, and these iterations will eventually stop when we see that there is no significant change occurring in the u of s, that is the expected accumulated rewards. So the moment the updates become negligible, we are going to stop this algorithm, and when the algorithm stops, that's when the rewards are going to converge and the corresponding policy will converge to the optimal policy, which is to say that u of s now represents the maximum accumulated reward that is possible. And the proof of this idea is given in section 17.2. A simple example to highlight how one can implement value iteration. Imagine we have three states, 1, 2, and 3, where the 3 represents the terminal state. And we can take two possible actions, A or B, in state 1 and state 2. And because the state 3 is a terminal state, so there is no action that makes sense because that's where the game ends. The corresponding rewards are -1 and -2. So if our agent or a robot is in state 1, the reward is -1 and it is -2 in state 2. The reward of state 3 is 0. We are also given the robot motion model probabilities, 8 of them. So these can also be represented by the state transition diagram. It's kind of a state machine diagram, which say that if you're in state 1 and if you take action A, then you will end up in state 2 with probability 0.8 and you will remain in that state with probability 0.2. Same goes with the state number 2. So if you take action in A in state number 2, then you will reach state 1 with probability 0.8, remain in the state number 2 with probability 0.2. But if you take action B in state 1, then you are more likely to remain in that same state, probability 0.9, but there is some small chance that you will end up in state number 3, which is the terminal state. Likewise, if you are in state 2, if you take action B, you can reach state number 3 with some small probability 0.1, but it is highly likely that you remain in state number 2 with probability 0.9. And our job is to compute the maximum expected accumulated reward U1 and U2 Pysteric for the corresponding states, and we need to find out the optimal policy using value iteration. So just to let you know, this is one of the end chapter problems of the value iteration, and I have written a Matlab code for that. The chosen initial values for U1 and U2 are -0.5 for each one of them, and the value of gamma is set equal to 1. Now after first iteration, as U's are updated, U1 is -1.5 and U2 is -2.5, and the corresponding policy says that you should take action A for both the states. After second iteration, the value of U1 and U2 -2.35 and -3.7 respectively, and the policy has now been updated. It says that you should take action B in state 1 and you should take action A in state 2. And as we proceed through the subsequent iteration, you will notice that the policy has remained unchanged, but the value of U, both U1 and U2, are still decreasing. However, after near 100 iterations, the value of U1 and U2 have begun to converge. Eventually, say around 120 or more iterations, U1 will eventually converge to -10 and U2 will converge to -12.5, and that's where you would like to stop the algorithm. The corresponding policy is the optimal policy, which is to say that you should take action B in state 1 and you should take action A in state 2. Now let us try to understand why does it make sense to take action B in state 1 and take action A in state 2. So first note that the reward of state 3, the terminal state, is the highest. Then comes the reward in state 1, which was -1, and the state 2 is least rewarding, but this reward is -2. So intuitively, the robot should try to reach the state 3 as soon as possible, because that is the only state which has a non-negative reward. So if the robot is in state 1, then it should try the shortest route, that leads to state number 3. So if you look at this diagram, from state 1 to state 3, if you take action B, you succeed in reaching state B with probability 0.1. So on average, it takes about 1 over 0.1, which is about 10 steps or 10 attempts to go from state 1 to state 3. And this is the shortest possible route that we can think of. And during those 10 attempts, on average, you will fall back on state 1 where the reward is -1. So on average, one can expect the expected accumulated reward in state 1 to be -10. And quite naturally, the optimal action will be to take action B. However, on the other hand, if we look at state 2 as the starting state, initial state, then intuitively, if we would like to go to state number 3 as quickly as possible, and here again the chances are very slim, the same actually, 0.1. So if you are in state 2 and you take action B, then you will need, as calculated previously, about 10 steps, 10 attempts, and in each attempt, it's a failed attempt, you fall back on state 2 where the reward is -2. So the expected reward, if you try to directly jump from state 2 to state 3, is going to be -2 times 10, which is 20. Therefore, if you're in state A, it is better if you first try to reach state 1, which can be done rather successfully using action A. In state 2, take action A and you can get to state number 1 with a very high probability, that is 0.8. So on average, it takes about only 1.25 steps to go from state 2 to state 1. And once you are in state 1, then as we learned previously, the best bet is to take action B and reach state number 3. So that's how the expected utilities make sense. Quite naturally, the expected accumulated reward for state 2 is slightly lower than -10. So it's -12.5 because of the minus expected reward in your effort to go from state 2 to state 1. That's about -2.5 on average. Next comes the policy iteration. It is a method for computing the optimal policy iteratively, but by linearizing the U pi of s expression till the policy pi converges. So similar to the value iteration algorithm, we're looking for convergence, but this time we are looking to converge pi rather than U. And the other important change is that we're going to linearize the expression, because the expression of U pi of s includes a max operator, the maximization operator, which makes the expression nonlinear. The policy iteration method is actually a two-step method. In the first step, we are going to execute the policy evaluation. In the second step, we are going to improve the policy. And these two steps occur in tandem in each iteration, and hopefully when the policy converge, it is the optimal policy. So in the policy evaluation step, we are going to update the policy by first solving the system of linear equations. So in order to make the system linear, we are going to drop the max. So you notice that there is no max operator here. So the max operator has been dropped. And what was that max operator doing? Well, it was actually calculating the maximum expected utility based upon the set of actions A. So the action that gave us the maximum expected utility was used. But here we don't have those actions coming out as a result of maximization. Rather, the actions are specified by the predefined updated policy. That's pi s1. So the moment we have dropped the maximization operator, we don't know the best action for that state, but we know the action specified or dictated by the updated policy. And this policy, this updated policy, was obtained from the previous iteration. So in some sense, in policy evaluation, we are going to fix this pi, and the action is dictated by the policy. So we are going to write down the expression of u pi s1, u pi s2, all the way to u pi sn. And we are going to have a system of linear equations. These are n linear equations. And if we solve them, we are going to get updated values of the u. In the policy improvement step, we are going to try a new policy pi prime based upon the exploration of new set of action which can possibly increase the expected accumulated reward of a given state compared to that computed in the previous iteration when the policy was pi. So this maximization is over the possible actions one can take in a state S, and if there is an action which increases the expected accumulated reward compared to that which was achievable with respect to the previous or the current policy pi of s, then we are going to update the policy for that particular state, that is pi prime of s. So this policy is going to be updated. That's why the name policy improvement, that we are going to update the policy from pi to pi prime of s based upon the action that gives us an increased expected accumulated reward in that state S. To summarize the policy iteration algorithm, here is the pseudocode. We're going to initialize pi and u, and at this point I should note that for the purpose of computation, the superscript pi is not required in the expression of u of s. So we are going to drop the superscript pi for the purpose of computation. So we are going to initialize two quantities. The policy, we can start with some randomly chosen policy, and the initial values of the expected accumulated reward for all the states that u of s is also initialized with some random values. Then we are going to start our iteration. So we are going to repeat this process till the policy converges. So till policy converges, we are going to repeat these steps. So what are these steps? First of all, we are going to update the expected accumulated reward for each state S by the execution of the first step of the policy iteration, which was actually the policy evaluation. So we are going to solve a system of linear equations to find out the updated values of u of s. We call this u prime of s. Then we are going to visit each state S, and for each state S we are going to see if we have a new action that gives higher expected reward for that state compared to the expected accumulated reward which was achievable from the existing policy, which is pi. So if there is such a action that we can take which can increase the expected cumulative reward, then we are going to update our policy as part of the policy update step we have just described. And so after going through several iterations, one can expect that at some point the pi will cease to update. It will not update anymore. And at that point, we're going to stop the iteration. And at the end of each iteration, by the way, we are going to assign u of s equals to u prime of s. And we're going to start over. And the hope is that when the algorithm converges, the value of pi is going to converge to the value of optimum policy represented by Pysteric. Let us solve the same three-state problem, but this time using the policy iteration method. So we are interested in finding the optimum policy using the policy iteration method. The robot motion model probabilities are the same, and the reward for each state is the same as before. So let's do a simple example using policy iteration. So based upon the Matlab code I have written to solve this problem using policy iteration, assuming the initial values of u's to be the same as before, minus 0.5, gamma is set equals to 1, and the initial policy should also be specified. So I assume that we start with the initial policy of taking action B for both state A, state 1 and state 2. And if you run this code, you find that after first iteration, the policy has been updated. So pi 1 is B and pi 1 is A. And after second iteration, the policy essentially remains unchanged. So which indicates that the policy has converged, and it has converged to an optimal policy, the one that we obtained from the value iteration algorithm. However, if we start with a different policy where pi 1 and pi 2 are set equal to A, and other initial values are kept same as before, then we find out that after first iteration, the policy has remained unchanged, and it remained unchanged in the subsequent iteration. So the pi has indeed converged, but the question is that has it converged to an optimal policy? So in this case, you will find out something interesting which has happened, that the algorithm has not converged to an optimal policy. And the main reason is that the policy evaluation step, the first step of the algorithm, in which we need to solve a system of linear equations, turns out that the system matrix is singular. Therefore, the system cannot be solved, and hence the algorithm is outputting incorrect result and the suboptimal policy. However, this singularity problem can be easily fixed if we reset the value of gamma. So if you choose the value of gamma, which is considerably smaller than 1, such as gamma is set equals to 0.7 in this case, and if you rerun the policy iteration algorithm for the two different cases, for the two different initial conditions, one in which the policy was that in both state 1 and state 2 take action B, and the other policy we tried was that take action A for both the states. So we find out something interesting, that in both cases the algorithm has now converged to an optimal policy, which is to take action B in state 1 and action A in state 2. And it has fixed the problem, particularly for the second case, in which previously we saw that for this particular case, when the initial policy was to go for action A in both the states, the algorithm failed to converge to the optimal policy. So here it is giving us the correct answer. So this value of gamma has a significant role to play as far as the convergence of policy iteration algorithm is concerned. I will share with you the MATLAB code implementing both the value iteration as well as policy iteration algorithms for the results that we have just discussed, and you will be expected to use that code to explore the impact of the value of gamma on the policy iteration algorithm. And you can also take a hint from that code to solve the textbook and chapter problem 17.8. Although it will be useful if you first try to solve that problem by hand using paper and pencil, and then write a code and then match the result of the dry run of the algorithms with the output of your computer program. The textbook reading material includes sections 17.1, 2, and 3. And there are certain terms that we haven't really touched upon and discussed them in detail, such as the Bellman equations, the Markov decision process, utility function, and decision theory. So you're expected to learn about these terms and these concepts by yourself. Obviously, chapter 17 will be helpful, but you can also take help from elsewhere in the textbook. Perhaps you can look at the chapter on the decision theory as well. Finally, a few words on the Q-learning. So throughout our lecture, we have assumed that we know precisely what are the robot motion model probabilities. And we said in the very beginning that we have a complete knowledge about the environment rewards that the robot earns as it goes from one cell to another, or the rewards associated with each state or each grid cell. But what if we relax those assumptions and we say that we don't have complete knowledge of the motion model probabilities, and we also say that, well, maybe we can have some information about the reward, but the actual reward when we reach a particular state, the expected accumulated reward may be different from what we have expected the moment we initiated our journey. So in both these situations, we come up against a new set of challenges. And the set of challenges says that we need to learn the environment model as well as the robot motion model simultaneously as we maximize the accumulated reward. So while we try to learn the policy, the optimal policy, and we try to maximize the accumulated reward, we need to simultaneously learn about the environment model as well as the robot motion model, and the algorithm, the approach for that is known as Q-learning, and this is basically a topic of textbook chapter number 21. But we're just going to describe some salient features of Q-learning because complete and comprehensive discussion is indeed beyond the scope of this lecture. So Q-learning essentially relieves us of following any particularly fixed policy. In fact, it really encourages improvisation. Actions are taken as we go and explore and navigate the arena. In fact, Q-learning is about learning a Q function which has two parameters, the expected accumulated reward as well as the action. So we are going to track the reward as well as the corresponding action. So Q function is actually a function of both U and A. The other important thing is that we are going to use the exploration function as part of the Q function. And an important characteristic of this function is that in the beginning of the navigation, it favors the exploration. And as we move on to the latter stages of the navigation, it is going to favor the maximization of the expected reward. And it is often called as the balance, finding the right balance between this maximization, also known as manipulation, and the exploration. And it works fine even if robot motion is not known a priori. So these attributes of Q-learnings make it particularly suitable in a practical settings where we have incomplete knowledge of the environment or the robot motion model. So whenever there are uncertainties involved, go for Q-learning. So with that, I would like to formally conclude this week's lecture, and I expect to see you in the question and answer session to be scheduled on Thursday afternoon at 3 p.m. So till then, take care and have a nice day. Thank you.